Hello to everybody and welcome to our new public lecture within the European program Strong 2020. So we have the pleasure today to have a special guest, Professor Sonia Bacca, whom will give a lecture bringing us into the heart of matter. Deborah, please put my slides on. Thank you very much. So once again, welcome to our channel. And let me, before leaving the floor to Sonia, tell you something about our European program, Strong 2020. So this European program is studying the nuclear interaction in the form of the strong force, strong interaction in the heart of matter, unveiling actually what happens in the nuclear interaction and in the hadronic, so-called hadronic interaction. This is our web page, which you can have a look to learn more about our program. And what we are doing is to study the strong interaction at the frontier of knowledge. Having received funding from the European Union's Horizon 2020 research program. We have started already back in June 2019, and we are approaching the end of our project. And the project, actually, it's a big one. It was bringing together many of the leading research group and infrastructure, not only from Europe, but also from other participant institutions. So we are embracing 14 European member states, one international European interest organization, which is CERN, and one European candidate country. But it's not only these countries, we have also other participants involved in the research, which are bringing together participants from 36 countries. And we are doing a lot of research divided in 32 actually work packages. We are developing technology, and we are also developing knowledge, as I was telling you before. And in this context, let me tell you that we are also offering access to 6 world-class experimental facilities. And these are in Europe. These are COSI, MAMI, LNF, ELSA, GSI FAIR, and CERN. And also to ACT STAR in Trento, which is a basically theoretical center for developing a strong interaction. And all these facilities do play a crucial role in fostering innovative theoretical development and experimental research in hadron physics. And this happens right now, actually, in Europe. This is a map of involved institutions from across Europe, which I was mentioning before. Moreover, let me also tell you that today we have a very special guest, who's Professor Sonia Bacca from Mainz in Germany, from Johannes Gutenberg University in Mainz. And she's going to bring us into the heart of matter. Professor Sonia Bacca is a theoretician, and she is working exactly to investigate the strong interaction at energies relevant to the theoretical interpretation of various experiments, including MAMI in Germany, but also in other accelerator facilities. If you want to know more about our program, just go to our webpage, stay tuned. And now I leave the floor to Professor Sonia Bacca, to whom I want to thank very much for being with us today. And to you, those who are looking to us today, if you have questions, please just write them into the chat, and we'll take care to ask Professor Bacca after her lecture to translate, to put her the questions which you are writing to us. So thank you very much, Sonia, to be with us, and I leave the floor to you.
Yes, thank you. Let's see, yeah. So thanks a lot for giving me this opportunity to present a public lecture within this Strong 2020 initiative. I would like now to take you through a journey where I will show you how we compute the heart of matter, being the nucleus in this case. So let's see how we get there. First of all, we are physicists, so we are interested in understanding the constituent of matter. And if we start from water, which we are all made of, and we try to look inside it by probing it with a shorter and shorter wavelength, what we discover is that water is made by molecules, that molecules are made by atoms. And atoms are not the indivisible particles that the ancient Greek were thinking of, but they are objects rather empty, I would say, where electrons, which are very light particles, orbit a denser core, which is the nucleus. The nucleus, which is the subject of this talk, is not simply this little ball you see there, but it's compound itself in terms of nucleons, the protons and the neutrons, which interact with each other, and which are themselves made by interacting quarks and gluons. So this is where we'll reach the fundamental level as of our knowledge today in particle physics. And I will concentrate in this talk on the nucleus. So I will look at a specific wavelength of the order of a femtometer, of a few femtometer, which is the typical size of these systems. So nuclear physics was born more than 100 years ago with the seminal experiments by Rutherford, who was shooting basically alpha particles, which are like nuclei of helium-4, through thin foils of gold. And he was seeing that most of the particles were passing through undeflected because, as I said, the atom is mostly empty. And some of them, though, were deflected by a large angle, meaning that most of the mass of the atom was concentrated in the center, which is the nucleus. Since then, of course, we have learned a lot about nuclear physics. We have discovered a lot, and we may put our knowledge on the famous chart of nuclides, which is this two-dimensional plot where we have the neutron number on the x-axis and the proton number on the y-axis. And each of these little squares correspond to a nucleus. So as you see, we don't have infinitely many combinations of protons and neutrons, but a finite number. And we know roughly 300 of them as stable nuclei, meaning they have a lifetime which is comparable with the age of the universe. So we haven't seen them decay. And these are the black dot that you see in the middle of this picture. Actually, all the other colored little squares are other nuclei which are unstable because they decay one way or another. And they have a shorter and shorter lifetime the more we go far away from the so-called valley of stability. We know roughly 3,000 then or more, but we expect there to be a lot more in the so-called terra incognita, especially in the neutron-rich region. So these nuclei have been formed at some point in the universe, but then decayed. So we cannot observe them anymore on Earth unless we produce them in a laboratory to study them. So, of course, we'd like to understand those nuclei as well. And finally, if we imagine to take an infinite number of neutrons and protons, we basically form a neutron star, and that's also an object that we would like to understand in nuclear physics. So what I would like to talk about today is how we try to understand the property of stable and unstable nuclei by describing them in terms of interacting protons and neutrons. There are a variety of ways to do that. I will focus on the so-called ab initio approach, which I will try to describe right now. So ab initio comes from Latin, means from first principles, and here the first principles are protons and neutrons. The starting blocks are protons and neutrons. So we're not talking about solving the nucleus in terms of quarks and gluons. It is possible these days. Several groups are trying that. And it can be done for very light systems. However, calculations have still large uncertainties. And here we would like to have to start from protons and neutrons and be able to achieve a precision that is comparable to the one of the experiment. So now if we take the relevant degrees of freedom of the scale of the energy scale of interest, which are protons and neutrons, then we have to solve a quantum mechanical problem because we are looking at the infinitesimally small. So we will have to solve Schrödinger equation for A nucleons, A being the sum of the protons and the neutrons. And such equation reads H psi equal E psi, where H is the Hamiltonian, E is the energy, psi is a wave function. So this Hamiltonian will contain the kinetic energy of the nucleons and their interaction, labeled with V. If we have these ingredients, then we have to solve that equation, and we can only do it numerically. Given the kind of interactions we have in nuclear physics, we cannot provide an analytical solution, so it goes only numerically. But it can be numerical exact for light systems, or if we want to go to the medium mass range or heavy nuclear mass range, there we have to introduce some level of approximation, which we, though, would want to be controllable. So we want to be able to provide uncertainty bars of our calculations. And since in the end, all these interacting protons and neutrons are put on a computer, which is a set of 0 and 1, that's the idea represented by the figure that you see on the right-hand side, which is a visualization of what we are doing, an artistic visualization, of course. So let me spend a few words telling you about this interaction V that describes the nuclear dynamics, the force between and among nucleons. The theoretical communities in the last few decades has converged towards the use of chiral effective field theory as a tool to construct interactions between and among nucleons. And the idea is based on, first of all, looking what is the fundamental theory, which is QCD, and looking at that Lagrangian, and then say, okay, I want to use, though, the effective degrees of freedom, which are the relevant one at a lower energy resolution. And starting from those, impose the symmetry, the very same symmetry that we have at the QCD level, which in particular is the explicit and spontaneously broken chiral symmetry. So we impose that symmetry on our effective degrees of freedom, which are nucleons and pions. And it turns out that if you do so, you can describe, for example, the interaction between two nucleons as being mediated by the exchange of a pion or more in the long range part. And in the short range, where the nucleons get very close together, then we are sensitive to this high energy degrees of freedom, which we don't resolve with an effective theory. And those are encapsulated into low energy constants, which are typically fit onto experimental data. For example, the nucleon-nucleon scattering phase shifts. Now, to make the long story short and simple, I want to highlight two important features of this chiral effective field theory. First of all, if you derive that theory for nuclear forces, you see that interaction between two nucleons are not enough, but interaction that involve simultaneously three nucleons, so-called three nucleon forces, appear naturally and consistently with the two-body force. Those are typically, so they also come with low energy constants, which are typically calibrated on a very light system, such as Triton, helium-3. And the beauty of an effective field theory approach is that it can be applied in a systematic way. So it is basically nothing else than a momentum expansion of your Hamiltonian or Lagrangian. And if your momenta are low, this expansion and is divided by a cutoff, which is a large momentum, this is an expansion that is supposed to converge. So you can do your theory at the leading order, then you can improve it and do the next leading order, and then improve it again. At some point, the higher order terms will not count anymore. So this is a very attractive feature of this theory, because it allows you to assess uncertainties. So this is what regards the dynamics between and among nucleons. However, we are also interested in understanding what happens if I take a nucleus and I let it interact in an external electroweak field, for example. There I need another ingredient, which is given also, can be derived within chiral effective field theory, and it would tell me how, for example, one nucleon, which is my degrees of freedom, will interact with an external photon, let's say. So you will have those terms. However, if you imagine that the interaction between two nucleons is mediated by the exchange of a pion, that pion can be charged. So it can also interact with a photon. So there will naturally be also so-called two-body currents, so terms that involve at the same time two nucleons. Okay, so also similar to what happens for the nuclear forces, also these electroweak currents will have several terms, one-body terms, dominant, two-body term, subleading, and in principle there can be higher order terms as well. Okay, so with these theoretical ingredients, we are now going to compute the heart of matter. And before I show you a few examples that I have selected, I wanted to convey the excitement about this field, because I think there are mainly three reasons why this field is now having really a renaissance. It's going very well. The first reason is that we are able to reach heavier and heavier nuclear systems. Traditionally, this ab initio approach was restricted to the domain of light nuclei. But in the last decade, or one and a half decade, we have actually been able to reach out to heavier systems. On the one hand, thanks to the availability of better computers, but also thanks to the introduction of algorithms that scale mildly as a function of mass number. And this is really playing a crucial role. So, for example, as of 2015, we were able to calculate calcium-40 or calcium-48, roughly 50 particles. And as of 2 years ago, 2022, people were able to calculate lead with 208 nucleons in an ab initio way. And that is the first time. This is this Nature physics paper that I report below, which I'm not part of, but I think is super exciting what was achieved there. The second reason why I think we are living in exciting times is that we are not focusing anymore just on bulk properties such as binding energy or radii of nuclei, but we can now tackle more and more dynamical observables. And with that, I mean we are looking at excited states, transitions, etc. And there, things are a bit different. So even simple things such as the alpha particle, which is a nucleus made by two protons and two neutrons. If you look at how you can transition from the ground state to its first excited state, which is a 0 plus, has the same quantum number of the ground state, yet is orthogonal. You can look at this transition with electron scattering. Well, if you look at that and you compare the most precise experimental data for that observable, which were obtained just last year out of an experiment performed here in Mainz, and you compare that with some chiral effective theory results, including mine, it is too high. It is unexpectedly not in agreement. So this was a puzzle and went into the news, into science popularization news, because it was unexpected, and has also triggered new calculations that now agree with experimental data when either continuum effect are included or where nuclear forces are simplified. Well, the puzzle is still on because there are other calculations with potential similar to the one I've used that still disagree with experiments. So we need to understand, but we nail it down to perhaps some subset of calculation that have this. And it's exciting because when you don't find agreement, you learn new things. And we'll see how it goes there. So finally, the third reason why I think we are living in exciting times for ab initio nuclear physics is that we can use now our knowledge on the nucleus and bridge nuclear physics to other fields of physics, such as astrophysics. I will make an example regarding neutron stars. And we can bridge also to particle physics. I will make an example with neutrino physics. And finally, we can also bridge to atomic physics. And I have an example at the very end of the talk. So now with this initial overview of what one can do with how one can calculate ab initio nuclei from ab initio point of view, I'd like to show you a few selected examples of things we have calculated recently, bridging here and there to other fields of physics. So the first example I've picked bridges to astrophysics, and it regards the first example of nucleosynthesis, which is the Big Bang nucleosynthesis. This is a process that takes place just a few minutes after the Big Bang, which is time zero, and it leads to the formation of the lightest nuclei, starting from deuterium and going all the way to lithium-7, but nothing else. So only the very light nuclei are formed in this process. And the very first reaction is the fusion of a neutron with a proton to form a deuteron with the emission of a photon. So this is in principle a simple process, just two nucleons, and the deuteron and the photon. So it has been in fact studied by many people, but just 2 years ago, together with Vijaya Acharya, former postdoc here in Mainz, who is now in the United States, we have looked at that with chiral effective field theory. And I would like to show you how, with this theory, you can actually assess uncertainty. So in principle, this chiral effective field theory provides you with expansion in momenta of your, in this case, two-body interaction. De facto, though, while the expansion should go up to infinity, we truncate it. So you could ask yourself, what is the error that we are making by truncating this expansion? Well, this is exactly where Bayesian analysis can come into play. And through that, we have given a statistical interpretation of the error that we are making by leaving out certain terms. And this is what is shown in this figure. On the left-hand side, you have the fusion cross-section. On the right-hand side, you have the opposite process, which is the dissociation, the photodissociation of the deuteron. And the calculations are performed at various orders. And you see that, for example, at NLO, which stands for next to leading order, the green band is quite broad. And that is an assessment of the uncertainty due to the higher order terms that we left out. And by the time we go to N3LO, which means next to leading order, this orange, in this case, band, it becomes much smaller and is of the order of 0.2%. And you also see that those bands nicely pass through the experimental data in this range from threshold to 3 MeV. In this energy region, the electric dipole transition dominates, and at very low energy, the magnetic dipole transition dominates. And if we look at very low energy, imagine that we zoom in at zero energy on the left-hand side plot. We look at there what we have in our most precise calculation, we get something like 7 in the appropriate unit. And then if we take the experimental value there, the experimental value is actually 7.3. So we have a 3% deviation, and we know why. The reason is that we have not included the famous two-body currents that I mentioned before, and we are working towards including them to improve this calculation. So now 3% is a small effect. I want to show you another example where these two-body currents enter and their effect is visible. So now I will make a second example, which is not necessarily connected to astrophysics, but is a pure nuclear structure application where we compare theory with experiment. So in this case, we look at lithium-6. So we go from 2 to 6 nucleons. It is considerably more complicated to do so, but it was possible. And this is actually the fruit of a nice collaboration that we have with the University of Darmstadt. So here, what you see is a comparison of experimental data and calculation. So the experimentalists in Darmstadt were able to measure the magnetic dipole transition from the ground state to the 1+ excited state of lithium. That's this horizontal, large, dark gray band. Okay, and then it's plotted versus the magnetic dipole moment, which is a ground state observable that is measured with higher precision, and it's just this vertical line. There you see some data there, some symbols, and these are the theory, not the experimental data. So on the one hand, if we don't include the two-body currents, we get the triangles, which are severely underestimating the BM1 transition strength. While if we do include these two-body currents, we get a cluster of 4 points, which are much better agreement with the data. So the difference in the 4 points are different parameterization of the chiral Hamiltonian, including 3 nucleon forces in this case. So you see here, the effect of these two-body currents is much more visible, is of the order of 10%, and it's needed in order to explain experimental data. All right, so I've shown an example of 2 nucleons and now an example of 6 nucleons. But what about heavier nuclei? Remember, I told you we can do all the way up to lead. So we have to pause a second here and think about what it takes to solve that. So we have to solve a quantum many-body problem, basically the Schrödinger equation H psi E psi. And this is an increasingly hard problem to solve. We can understand that if we imagine to solve it by expanding our wave function psi in terms of a basis. And the most common, most beloved basis in nuclear physics is the harmonic oscillator basis. Well, it turns out that if we want to do such an expansion on a nucleus such as oxygen 20 or 22, we easily reach matrix sizes of the order of 10 to the 10, which is incredibly large. So while we can do that, if we have better and better computer, this is of course not the way you can do lead. The reason is that the scaling of this algorithm as a function of mass number, it's exponential or factorial. We need to go to something else. So what next? You have a choice here. These days you have a choice really. Either you try to introduce and invent new many-body methods which have milder scaling of their algorithm as a function of mass number, perhaps polynomial scaling as opposed to exponential scaling, or you resort to quantum computing. Quantum computing is an emergent technology which will allow us at some point to solve a quantum system on a quantum computer. And while we are not there yet for the real many-body nuclei, several of my colleagues are devoting some of their time to devise the best algorithm which can translate our problems into something that is computable on a quantum computer. I myself have more looking at these polynomial scaling methods, and in the last 10 years or so, I've been focusing on using couple cluster theory as a polynomial scaling method to solve a many-body problem. Interestingly, couple cluster theory was invented in the 50s in nuclear physics. Then it became the workhorse in chemistry, and now it's having a renaissance again in nuclear physics. So such theory starts from a Slater determinant, which is an uncorrelated state, just an antisymmetrized state of single particle states. And starting from that, you can imprint your correlation with an exponential ansatz, e to the t. T is itself expanded into clusters. That's where the name comes from. And T can be a one-body operator that induces one particle, one hole correlations on top of your Slater determinant, or it can be a two-body operator inducing two particle to hole correlations on your Slater determinant, and so on and so forth. In principle, if I expand my T up to a particle, a hole, I will obviously have an exact theory. But in practice, it is too complicated to do so, so we resort to approximations. And the most commonly used approximation is that where we truncate T to being just one particle on hole plus two particle to hole correlation. This is called CCSD, which stands for coupled cluster singles and doubles. Now, if you look at the fact that this operator is in the exponent, I can imagine to Taylor expand my exponent. So I will have also terms like that go like T2 square, which effectively will simulate part of the 4-particle 4-hole correlation. So de facto, just because you have this exponential ansatz, this is a very good approximation of your ground state. You can capture something like 90% of the correlations within this approximation. And it is also clear how to improve upon this approximation by adding triple corrections. Typically, what we observe is that then you can get 99% of your correlations. And the advantage of this method is that it scales polynomially. So in the specific, for the case of couple cluster single and double, we're talking about something that scales like number of nucleons to the power of 6, which is much, much better than an exponential. So that's why you can go all the way to lead to do these calculations. And even if you capture just 99% of the physics, that's much better than anything else on the market. Okay, so now, given this very powerful theoretical tool, I would like to show you some applications, and I chose to present something in relation to astrophysics, in particular in relation to neutron stars, which are very famous, very interesting, especially after the discovery of gravitational waves signal. So we have seen that not only we can detect gravitational waves from binary black hole mergers, but in particular, what is interesting for nuclear physics is the fact that we can detect the signal from binary neutron star mergers. And so we expect to learn a lot more about neutron stars, in particular about the nuclear equation of state from these gravitational waves. On the other hand, you can look at the equation of states also by studying properties of finite nuclei. So the equation of state is nothing else than an equation that tells you the energy per particle of an infinite system expanded around the case of pure symmetric matter, when you have a little bit of an imbalance between neutrons and protons. That equation there, you see that the first term with the unbalance of neutrons to protons is called the symmetry energy and can be expressed in terms of two famous parameters, J, called the symmetry energy, and L, called the slope parameter. Well, these two parameters can be nailed down or constrained better via the study of finite nuclei. In particular, one observable that is known to be very sensitive to it is the so-called neutron skin thickness, and lead 208 is the favorite nucleus to look at that. So it is a neutron-rich, stable nucleus, and when there are more neutrons than protons, what happens is that the neutrons like to stick outside of the protons, forming a kind of a skin. And so theoretical calculations tell us that this observable is very correlated to the symmetry energy parameter L. And this is what you see here in the plot that shows calculations from density functional theory with the triangles, and also calculations from ab initio theory with the blue dots, which come from the Nature Physics paper that we mentioned before. So clearly, if there is such a correlation which is seen by more than one theory, if you can measure the neutron skin thickness, you can infer constraints on L, on this parameter of the equation of state, so you can learn about neutron stars. And that's precisely what is being done. There is another observable that is correlating very much with this equation of state parameters, that is the electric dipole polarizability, which you see on the y-axis of this plot is called alpha d. What this observable tells you is the probability I have to polarize my nucleus if I put it in an electric field. What will happen is that the proton, which are charged, will be displaced and will oscillate, for example, against the neutrons. How much this happens, it's the quantity that this polarizability measures. And if we look again at lead 208 and we compare calculations from density functional theory, again with the triangles, and ab initio calculations with the blue dots, we see that there is a correlation also here. Again, if we are able to measure the polarizability of this nucleus or others, we'll be able to infer constraints on the symmetry energy and the slope parameter, in particular the slope parameter. So where do we stand today, especially in comparison to ab initio nuclear theory? So let's start from the neutron skin thickness. So this is a very complete plot. I want to explain it slowly. First of all, the best way to measure the neutron skin thickness is to do parity violating electron scattering, because it relies on electroweak interactions for which we can use perturbation theory. We can be the least model dependent. This is what has been done so far at Jefferson Lab for calcium-48 with the experiment called CIREX, which is this green point you see on the left-hand side. And it has also been done for lead with the experiment called PIREX 1 and 2, which is again this green point on the right-hand side figure for lead. All the other black points that you see there are other measurements of the skin obtained with hadronic reactions, which are plugged by larger uncertainty or less, let's say, unknown uncertainty sometimes. So that's the important difference. However, if you look at them and you then focus on the lower part of this plot where I have the magenta squares that show the ab initio calculations, you see that for calcium-48, the ab initio calculation agree with CIREX, definitely, and also with the other points if you want. We have performed ourselves the first calculation of the calcium-48 skin in 2016, and now it's updated with new interactions as of 2022, and the two calculations are consistent with each other. If you now focus on lead on the right-hand side, we see there that the ab initio calculation at the very bottom there, it's predicts a bit of a smaller skin with respect to what it's measured in PIREX. It's not a huge deviation, let's say, but they, within the respective 1 sigma error, they are not compatible. And on the upper part of that plot, you see also the constraints we have from gravitational waves and from X-rays with NICER, and they also prefer smaller values of the neutron skin. So we are excited to hear what will happen with the MREX experiment, which is planned to be performed here in Mainz at MESA, the facility we are building. This experiment is based also on parity violating electron scattering and will reduce the uncertainty by a factor of 2 with respect to PIREX, and of course also the central value can change, so we'll see what happens there. But the message is, as of now, calcium-48 works well. On lead, there is a slight tension between the ab initio and the PIREX measurement. So what about electric dipole polarizability? So here, instead of showing all the possible measurements of the various nuclei, I decided to show only one picture, which stems from our own calculation in collaboration with Francesca Bonaiti, my student, and our colleagues in Darmstadt. This is actually also a very nice combination of an experimental and theoretical paper. The experimentalist measured the electric dipole polarizability of calcium-40 and 48, leading to these light blue bands that you see horizontally and vertically. And the figure shows on the left-hand side theoretical results, which are these dots with error bars, obtained with ab initio methods, and on the right-hand side, calculations obtained with density functional theory. And in both cases, we see a clear correlation between the two quantities, as expected. There are some potentials, for example, the black dot on the left-hand side falls exactly in the middle of the experiment. And also on the right-hand side, you could identify like the purple region that is in best agreement with the experiment. And combining this knowledge on the finite nucleus together with a nuclear matter calculation, you can infer values for this parameter L, which we obtain as being between 41 and 49 MeV, which is compatible to other constraints found previously. All right, so I think now what I would like to do is go a step further and talk about how do we calculate actually reactions in medium mass nuclei, in heavier nuclei. And what I mean is that I would like to see what happens if I take a nucleus and I let it interact with an electron or a neutrino in providing via this probe some energy to my nucleus so that the nucleus can actually break. So those cross-section can always be described in terms of response functions, which is the first equation you see up there, that includes expectation values of our current operator, which we mentioned at the very beginning, calculated between the ground state and the excited state psi f, which are in red there. So these excited states of the nucleus can be bound states, but they can also be in the continuum, because if I have enough energy, I can start kicking out nucleons. For example, with 8 MeV of energy, I can typically kick out 1 nucleon. With twice as much, I can kick out 2 nucleons, and so on and so forth. And an exact calculation of this state psi f in the ab initio sense for all these different channels is out of reach presently, unless we restrict ourselves to at most 5 particles. So for the all the other nuclei heavier than that, either you resort to some kind of approximations, or you do a sort of detour, which is what we propose. Instead of calculating the response function, we want to calculate an integral transform of it. Think about the Fourier transform over Laplace transform, which are very familiar in sciences. So we use here a different kernel, which is a Lorentzian curve. But apart from that, if we do so, we can prove that in order to calculate this transform, you need to solve a bound state-like equation, which I report there for completeness. But the message is that equation can be calculated also with couple cluster theory. So you can access in this way medium mass nuclei and calculate a reaction for it. And I would like now to focus on the applications, which are simpler to understand, and the place where we have used most successfully in recent times this idea is in the field of neutrino physics, which is more, say, a particle physics field, but where nuclear physics plays an important role. So let me mention that the interest here is in understanding neutrino oscillations. We know that neutrino have mass, so they oscillate. There has been a Nobel Prize awarded in 2015 for that, for the discovery of that. So if we have a neutrino with one flavor, it does change the flavor, its flavor in time. So it is like if you are at a party and you are given a cocktail made with orange flavor, and while you sip it through time, at some point the flavor changes and you can taste a little bit of a lemon and a little bit of lime. And this is not because you are getting drunk, but it's because the flavor of neutrinos changes. This hypothetical cocktail is like a neutrino cocktail. Okay, so we need to understand how this flavor change, and that in physics can be done through via the next generation long baseline neutrino experiments. The major players here being Hyper-K in Japan and Dune in the United States. So here what happens is that a neutrino is being created at a certain point, then it is traveling through Earth for several hundreds kilometers. And it is then detected later in a far detector. And out of this information, you have to reconstruct the neutrino energy to then learn about the oscillation parameters. So effectively, what we need to know is how a neutrino interacts with the nucleus of the detector. And the targets here that are interesting are carbon-12 in case of plastic scintillators being used as detector. Oxygen-16 is interesting when water is used as detector, and argon-40 is interesting where liquid argon is using as a detector. The difficult thing here is that the neutrino has a very broad spectrum in energy that ranges from 0 to 3 GeV in case of Dune, for example. So there is no way we are able to do that with ab initio nuclear physics with our description starting from protons and neutrons. But I think that this approach has a window of opportunity in the low energy spectrum of this process, where we have giant resonances and all the way to the quasi-elastic peak. I think this is where we can provide calculations with quantified uncertainties, which then later could be put on in event generators to analyze the data. Okay, so what we have done so far is some calculation of electron scattering and a little bit of calculation of neutrino scattering. De facto, we would like to develop a theory that can do both, because the two processes have very strong similarities. In fact, they both share the response to vector current, while neutrinos also have, in addition to that, the response of the axial current. So we would like to calculate them both, and then would like to use new experimental data on electron scattering as a check of the theory before it is being used for the neutrino. And those experimental measurements can be done and will be done in mines. And the reason why you want to check electron scattering first is that with electrons you know exactly the energy of your beam, so you can be much more precise in your measurements. So it is a very strong check on the theory, necessary check of the theory. So I'd like to show some applications that we have produced so far regarding the electron scattering of calcium-40. So calcium-40 is per se not an interesting target for a neutrino, but it has the same mass, 40, as argon, and argon is an interesting target. We wanted to show here that you can use ab initio calculations to target mass number 40, which was never done before. In fact, this calculation was published on Physical Review Letter. This is also pioneered by Arshia Sobchik and Vijay Acharya. And if we look at the left-hand side plot now, you see two different calculations with two different potential in agreement very nicely with data. And if we didn't use all this machinery we have developed based on the integral transform and couple cluster theory, we would completely neglect the so-called final state interaction and obtain the so-called plane wave impulse approximation, which is this dotted curve that you see there in black, that is missing the data. So we do need that very hard technology in order to describe data. On the right-hand side, you see a very freshly published paper where we did the transfer response, and we also obtained a very nice agreement with experiment, and I shall say unexpectedly, because we were expecting to be lower than experiments, since we didn't include yet these famous two-body currents. So it remains to be seen whether two-body currents here are smaller or what. Work is in progress in that direction. Next, if we want to move to higher momenta, higher energies, we have to simplify the calculation by doing the plane wave impulse approximation, which does work at high energies. And this can be done through the spectral function formalism. This is the project that Ajay Sobchik is leading. And you see on the left-hand side a calculation of the electron scattering on oxygen-16 this time. So we went lower in mass, but oxygen-16 is an interesting target for the neutrino case. And you see on the left-hand side the comparison to electron scattering data. On the right-hand side, you see the application on neutrino scattering of oxygen-16. There we have T2K data. These are the data showed in the plot. And what Asia did here is to implement the spectral function, which is calculated from couple cluster theory here, into the Nouvre event generator, which includes a lot more of dynamical information there, which are left untouched. And the only novelty is the spectral function, which leads to these purple curves, which are in nice agreement with experiments. So this gives us confidence that the theory we are developing is very good. Okay, so this is what I wanted to say for the application to particle physics. And before closing, I would like to show this very last example, how we bridge the knowledge of the nucleus to atomic physics, this case. And in particular, I want to focus on ionic atoms. So what are they? They are exotic atoms where one electron is replaced with a muon. The muon, we can imagine it as a very heavy electron. So the best known such atoms are the hydrogen-like systems, where you have only one lepton orbiting the nucleus. So it would be one electron in case of an ordinary atom, or one muon in case of a muonic atom. So that one muon is much heavier than the electron, roughly 200 times. So it orbits much closer to the nucleus, and therefore it is more sensitive to the properties of the nucleus. So de facto, every spectral line of muonic atom can be expressed in terms of a QED part, which is typically well known from quantum electrodynamics, plus corrections due to the nucleus. And the nucleus leads to two major corrections. The first one is due to its finite size, the fact that the nucleus is not a point-like but has a finite size, 1 centimeter or so. And this is much larger in case of muonic atoms than in ordinary atoms, and that's why muonic atoms are used to extract, for example, the size of the charge radius of a nucleus. The next correction, which is smaller but nevertheless cannot be neglected, it's due to the internal degrees of freedom, which you can call it a polarizability correction. And here I had an animation which doesn't work, but fine. So what it means is that while the muon orbits around the nucleus, the muon has an electromagnetic field. So it will de facto deform the nucleus, which has internal degrees of freedom because it's made by protons and neutrons. The proton will follow somehow the muon, and as such create a kind of a dipole moment, and those effects change the energy level. So we need to account for them if we want to do precision physics. And this is the part that we can calculate very well. We have developed techniques to do that based on this time few body methods. It's not couple cluster theory, it's another basis function expansion, which works very well for 3 and 4 body systems. And we have looked at these nuclear structure corrections using chiral effective field theory at various orders, leading order, next leading order, and so on. And we have then used Bayesian uncertainty quantification to provide a statistical interpretation of our results, obtaining distribution of the probability for these observables. And apart from the details, we now want to embed this technology, this theoretical technology, let's say, into an interesting problem, which is called the helium isotope shift puzzle. Okay, so isotope shift normally means a difference between two radii. In this case, we are talking about the charge radius of helium-3 and the charge radius of helium-4, which are slightly different because they are different nuclei. So this can be measured with ordinary atoms, looking namely at the isotope shift. So you look at the difference between two electron energy level. you measure for, you know what it is for helium-4, and then you look at the difference when you change the nucleus inside your atoms. And you can access this information actually directly. You access directly the difference. And that's the black point you see at around the value of 1 femtometer there. The units are missing is femtometer. And you can also actually use muonic atoms to extract these radii. Muonic atoms, the lamp shift allows you to extract an absolute value of the charge radius for helium-3 and helium-4, but then you take the difference. And you obtain the green point there, which turns out to be different from what is seen in ordinary atoms. So there is a difference of 3.6 sigma, which is relevant, needs to be understood. And at the moment, we don't know exactly what the reason is. What we did is to calculate nuclear structure corrections for muonic atoms and ordinary atoms within the same theory and apply to the include this information into this experimental data. And what we obtain is now the red points, where we see that the 2 points are now further apart from each other. So this discrepancy goes from 3.6 sigma to 4 sigma. So it is enhanced. So it is not explained by theory. And our conclusion is that most likely here there are some systematic uncertainty that are not yet fully understood on the experimental side. Okay, but I think this is a nice example where you can use your nuclear physics calculation and make it relevant for atomic physics. And with that, I would like to conclude by saying that remarkable progress has been done in ab initio calculations. I've shown many examples, and that in particular, the study of electroweak processes allows us to connect to other fields of physics, which makes it very exciting. So I would like to thank all my collaborators, in particular all the young people I had the privilege to work with. I mentioned a few, there are many others. And finally, I would like to thank you for your attention.
Thank you very much. It was very fascinating what you are doing, and the progress which has been reached in this last year it's really impressive. Now I'd like to ask the people who are following us, if there are any questions, please put it in the chat. Meanwhile, I take the privilege to be here with you and to ask you, what would be your dream in this respect? So what would you like to calculate in the next, let's say, I don't know, 5 years time scale? What's the possibility, what you can hope on this?
So I really would like to push these neutrino calculations all the way. We have just started to do that. And that requires, for example, to look at argon 40. So I've shown you examples in the very last part of calcium 40. Calcium 40, from the nuclear physics point of view, is simpler because it's a closed shell nucleus. Argon 40 is not, so this requires substantial new developments of the coupled cluster theory. But then it can be applied to this interesting topic, and I think that's one of the things I want to push for. Then there are many other ideas. For example, looking at muon capture could give you a handle on the weak part of this interaction, which you don't check, for example, with electron scattering. So you need another experimental constraint to validate your theory.
And related to this, can I also ask you, so I was looking in the muonic atoms. I also work in exotic atoms, in the kaonic atoms, where there is also a puzzle because, well, in that context, different type of kaonic atoms gives you the kaon mass, which is 5-6 sigma far away. But so you would be imagining that that's an experimental issue, right?
So regarding kaonic atoms, I've not really looked into it deeply.
No, forget kaonic atoms.
Muonic atoms, you think?
Yes.
It depends on what. This isotope shift puzzle, probably. But so you would say, as a theorist, it's very easy to say, right? So I'm blaming the experimental.
That's right.
What I want to say is that we did the best possible theory as of now. We didn't find anything that explains the discrepancy. which doesn't mean that in the future someone will find something, right? So it is always possible, but at the moment, the state-of-the-art theory suggests that the problem is not in the theory. And if you look at this isotope shift puzzle for helium-3 and helium-4, it has a very long history where experimental data, even from similar, same group, moved over time. So I think these are super delicate experiments, and it is not easy to have all the systematics under control. So it is okay that so you do it step by step, right? So you do the
Sure.
best, and you find out actually this is a bit different, so let's do it again. At the moment, my feeling is that it is in the experiment, but you can never know. And in fact, so the muonic atom story, so they are very famous for measuring the size of the proton, right? So they got a very small value, and now we think that's the correct value. So
Absolutely. And do you need more computing power? Is this an issue in your field?
so yes, the better computer we have, the more we can do, but it's not just computer, right? So
Sure.
it is also development of algorithms, and that's where you need more people brains that work on than actually the computers. So we need computer, yes, but we need also new ideas on how to make things faster. Especially now, we want to explore a variety of parametrization of these forces. So once, I mean, even if I think about my own story, so like 10 years ago, we would do one calculation, and now we have to do the same observable, one calculation with a potential. Now we have to do 150. It's a completely different story. So yes, we do need more computer, but we also need more ideas how to speed up things.
That's cool. Is there any question once again? I don't see questions, but I see some thanks from some of our colleagues, Dominique Marchand, Angels Ramos. Yeah, some nice words from Julian Barbuscio. And so, Sonia, now I may hope that some young people it's watching us. So if you would be to encourage them to go into this field, what would you tell them? So, but because there is, yeah, it's easy to speak about black holes and things like that, but nuclear physics, and hadron physics still requires a lot of effort to be understood. So, if you feel yourself like giving a kind of a message to the young people, why should they go to study?
I think it's still a very exciting field to work on, where you can have your hands on, either on the theory side or on the experimental side. And what makes this field particularly nice is that there is a very strong interplay between theory and experiment. You don't have that all the time. So in other fields that are typically more separated. Here, I mean, I have a lot of collaborations with experimentalists. I'm not doing experiments, but I learn from them what their problems are, and I have the pleasure to explain them the theory. And I think out of that we become richer and more knowledgeable in physics. And that is something very particular of our field, I think.
I can only agree with you as an experimentalist. So I fully share your message and the progress which is being done in the last years by this very, very fruitful collaboration. So I also invite Deborah with us. So Deborah Bifaretti, if she's, hi Deborah. So
Hi.
Deborah was practically organizing our seminar today, our public lecture. She's from the Education and Dissemination Group of Frascati National Laboratory of INFL. Grazie, Deborah. Thank you very much.
Welcome.
And yeah, so once again, Sonia, thank you very much for being with us and for agreeing to give this lecture.
Thanks
and
to you.
To all the people who were with us today. And yeah, I can tell you that we are organizing the next lecture. We will receive some information in due time, and we wish you all a very nice afternoon and new week. Bye-bye to everybody.
Bye.
Bye.